Yeah.
Okay.
Yeah. It's working. Okay. Thank you, Trin. Also, Gunther, for the introduction. And hi, everyone. How are you doing? Good evening. I hope that you are doing well during this difficult situation. I should have been there for the lecture exchange, but due to this situation, so we have so many limitations. And then I'm still really happy. It's a pleasure to be here to give you a little bit what we are doing here related to our CNRD case study. And before I start, let me share my screen. Is it appear already?
Yeah.
Okay,
Good.
so let me introduce myself. My name is Hendi Fathur Rahman. You can just call me Hendi. As Trin said, that I'm a lecturer from Universitas Gadjah Mada, majoring Geographic Information System. And at the moment, I'm also working with CNRD related to the ongoing project. And in this occasion, I would like to present what we have been doing here in Indonesia related to the project. And this project is related to the disaster risk reduction in the coastal area of Yogyakarta. Yogyakarta is the province where our university is located. You can hear me clearly, right? Okay. And the title of my presentation will be High Resolution Geospatial Data for Disaster Risk Reduction in the coastal area of Yogyakarta. So this is the framework of the regional analysis of the course actually, but in this presentation, I will not deliver all of this framework, only few about the methodology and also the materials that we are using for collecting the data, especially providing hazard map in the coastal area. Because actually this project is still going and we are also still how to say, it's like preparing the whole material for the course, as I mentioned in the previous meeting with Trin and Gunther and also all the CNRD members in the network, that we are still how to say, like preparing all the materials and also modules. So actually this project is still ongoing and we are still collecting the data and we are still doing analysis, writing reports, etc. So I will present to you like what we have done during our project till now. So the outline is the case study introduction. So first, we all know that coastal communities is like one of the most communities that are in a high risk, and like most of the big cities, they are located in the coastal area, near the coastal area. And here in Indonesia, more than 4.35 million people that located in Sumatra, Java, and Bali are exposed to tsunami hazard. Here on the right side, you can let me minimize how to minimize this. On the right side, you can see the population that living in the tsunami prone area here in Indonesia, more than 5 billion here. But in the three biggest island in Indonesia is 4.35 billion. So here we can conclude that most of the people that located in the coastal area of Indonesia is living in a tsunami prone area. And you can see on the map here, this is the earthquake and seismic gaps map in Indonesia uh, that recorded until 2008. And in this figure, you can see code like SG1, SG2, SG3 to SG8. This is indicating the seismic gaps. Seismic gaps is where and the earthquake is not oftenly occurred. But these seismic gaps are potentially trigger a really big earthquake that because we are located adjacent to the subduction zone. So there is a mega thrust earthquake that potentially trigger like a huge tsunami. So most of the people that located in the southern coast of Indonesia, especially, or alongside this ring of fire, of course, they are really vulnerable. And then, as you can see here, the magnitude, this is the tsunami, the earthquake that occurred in 2004, which triggered like one of the most severe tsunami in the history. Uh, and then the southern coast of Java. Java is like the most populated island in Indonesia. Almost 60% of the population of Indonesia is located in Java. Despite the size of the Java is only 6% of the total area of Indonesia, but this is considered also as the most populated island in the world. And uh, it's also considered as the most at-risk area in Indonesia because the population density and most of the big city is also located in the southern coast of Java, which is facing the Indian Ocean. And then we are going to be more specific in Yogyakarta. So Yogyakarta is also one of the smallest province in Indonesia. We are regarded as a special province of Indonesia because we are still led by the king, while all the administrative unit at the provincial level in Indonesia led by a governor, but we are still led by the king. So we have the uh, how to say we are regarded as a special province of Yogyakarta, and uh, Yogyakarta is really famous with the tourism activity, and one of the most tourism activity that give us a very huge income to the local governments are tourism, and most of the sorry are coastal tourism, and most of the nice beaches, nice schools is located in Gunungkidul region, which is one of the region that located in the eastern part of Yogyakarta. I will show you the map. This is the one of the aerial photograph from the coastal area located in the Gunung Kidul. As you can see here, there are so many buildings here that located really close to the beach because most of these buildings are tourism facilities. And with many people being exposed to the tsunami hazard potential, evacuation planning must be carefully designed. But the problem is the the bureau that in charge for disaster management is not really how to say not really pay attention on the management disaster management action. For example, here in some beaches area they install tsunami evacuation and hazard map in the how to say in the gate before we are entering the beach. But the thing is that map the map is not how to say I would say this is not so clear and give biased information. And this is because they use low quality data sources. They only use national topographic map with medium to low resolution, and then the modeling is also inappropriate. For example, in this area, they make a tsunami inundation model, so they decide the evacuation shelter and evacuation route, but this model is inappropriate, I would say, because it's covering almost the whole area only based on the contour map. So they only filter the contour map that the area that less than 25 meter, and they decided that area to be like the hazardous area that people cannot like it's only limited, something like this. But actually it can be improved. And because of these inaccurate and inappropriate modeling, whenever they decide the evacuation point is quite difficult to access. Like it's not accessible because the most important thing in tsunami evacuation is the evacuation time, where we have to evacuate. We have to find safe place as fast as we can, because from the previous research, the tsunami that occur in the southern coast of Java is considered as near field tsunami. And near field tsunami, it means that the tsunami source is really close to the coastline, and it will reach the coastline less than 30 minutes. And during that short time, 30 minutes, we have to have our like how to say, we have to disseminate the information to the tourists or to the people that live in the coastal area that tsunami is coming. We need to have like uh, alert, like tsunami alert. And it is calculated that the effective time is only 11 minutes for the evacuation. And whenever the Bureau of Disaster Management plotting their um, shelter, tsunami shelter, this is very far, like more than 2 to 3 kilometers from the coastline. And then the thing is that the most effective evacuation is by the foot, and you cannot reach that place with only 11 minutes available. So in this project, we are proposing to provide more appropriate model, more accurate model using high resolution spatial data that acquired using unmanned aerial vehicle. This is the island of Java. So this study focus on the coastal area of Gunungkidul, as I told you. This is the province of Yogyakarta, and this screen indicates this region. And at the moment, our study is focused on this area because in this location, in this area, there are about 13 beaches, like 13 tourism beaches that very famous in this area, because most of the beaches is not so famous because it's quite difficult to access them since they are so far from the city center. So this area is considered as the most popular. So we focus our research in this area. So here in this project, we are implementing the use of unmanned aerial vehicles, or it's popular as drones. So we create an orthomosaic image, or we can say UFE photogrammetry. That this is one of the sub focus in photogrammetry is small format aerial photograph. So the reason why we are using this, because this is affordable, especially for the institution like university or ministry. Is not so. It's not even expensive to afford all the vehicles and all the materials to carry this project, because this is very cheap. And then, for example, this one, it's also feasible. It's not difficult to conduct the project, and you only need like a few member of teams, like 3 to 5. So not so many people are involved in the project, so it's quite feasible. And then it's easy to how to say, to organize as well, and you can also go to the field with really short time interval, just like how to say, like you can do it as often as you want, because it's really easy to be conducted. And the most important thing is it provides high resolution spatial data. I'm sorry if you hear some noise here, because right now it's raining. so hard here. You can see also the thunder maybe. And since I'm at home, maybe you can also hear some noise from my kids. There are two small kids here in my home. So uh, at this time, normally they are so noisy and so loud. So I'm apologize for that. I can show you one of the example of the aerial photograph that acquired using a UAV. This is one example of the products from the UAV photogrammetry. As you can see here, you can clearly see the area that covered in this aerial photograph. You can see the different land use. Like this is from this pattern, you can conclude that this is a school building, for example, and this is a football field, and this is cemetery, this is settlement, something like that. But we can go more like this one. We can still zoom it in. As you can see here, you can see like two or three ships here, and you can see cemetery. You can differentiate among trees with different patterns, something like this. But you can still zoom it in again. You can still go with a higher resolution like this. Like you can differentiate here. For example, this is very typical pattern for moss here in Indonesia. The moss is normally like this with this stage roof, something like this. We can differentiate it with the normal building like houses. And we can also see the banana trees here. We can differentiate it with the coconut trees, for example, even though the pattern is similar, but the size is different. So we can conclude that they are different trees. But we can still go to be more accurate again, something like this. If you have time, you can even like count the roof, and we can also differentiate like the roof that made from this one clay, and also that made from zinc, something like this. So this is one of the advantage of using small format aerial photograph. And maybe I'll go not so specific here. These are the type of aerial photograph based on the camera angle. So there are three different aerial photograph based on the camera angle, which are high oblique and low oblique, and also vertical view, something like this. In the high oblique, you can see the horizon, something like this, because this is really oblique. And the low oblique, you cannot see the horizon. And vertical is where your camera is perpendicular to the land, something like this. This is the illustration. This is the vertical view. This is low oblique, and this is high oblique. And here in this project, we are using the vertical view angle, because the vertical view is considered the most accurate with the lowest error. As you can see here, there are two different type of photo. The first one, this is the single photo that captured using the drone. Only one single photo, and we this is the center, the central projection image, which has the perspective projection. But after we process the image using a photogrammetry software, uh, it will create a orthomosaic image which has orthogonal projection. Actually, these images look similar, but it's different. As you can see here in this building, you can see the body of the building, the side of the building, but with the orthogonal projection, you can only see the roof, something like this. This is the illustration. For example, the camera is located here, and it captures this area. When the camera will provide you orthogonal projection after you how to say, combine a few overlapping images. I will show you later on, something like this. For example, this is these two pictures. It looks similar, but it's different. This is the single image central projection, but the second one is the image that already processed using photogrammetry software. You can see the difference here. For example, in the single image, camera will be focused in the nadir here. So this area will have the highest accuracy for the measurement, but there will be some errors from the area that located far from the nadir. As you can see here, this building is obviously we can see it from above, like we can only see the shape of the roof. But here in some building that located in the corner, you can see the side of the building, something like this, and it's also not not asymmetric here, but here is everything is symmetric and looks from above. So how to conduct this project? So first, we need to set our mission planning. So we are using something like this. We are using two different types of UAVs or unmanned aerial vehicles. The first one is fly wings. It can fly autonomously, and most of the body is dominated by the wings. So we call it fly wings, or sometimes fixed wings. And we use it for our first data acquisition because it could cover broader area with longer flight time. But we also like renew, we capture the new image of different bits regularly, like every 1 year. So we use smaller UAVs. This is the multi-rotor type, DJI Phantom 4. I think this is really common. So first we are setting our flight route. As you can see here, this is the software that we use. It's called Drone Deploy. We can set the altitude of the drone here. We can set the direction. We can set the flight speed. We can also set the overlap. This overlap is really necessary because uh, when the all the images have good overlaps, covering the whole area in good overlaps, so it will provide us really good accuracy of UAV photogrammetry. I will show you in the illustration. And beside the flight route, we also need a ground control point. Ground control point is a terrestrial coordinate that we measure using geodetic GPS. So like high accuracy GPS, because we need to uh, set the coordinates from the aerial photograph. This is an example of a different flight route. This is also, you can see clearer here. The front overlap set into 75%, side overlap 65%. The flight direction is also necessary because sometimes we need to how to say, understand the wind direction, because when the wind direction, also wind speed is quite high, and it's heads to specific direction, we need to adjust our flight direction. Otherwise, our aircraft will be facing the wind, and it's quite difficult to move. Sometimes it will be, how to say, it will be moved outside this route when the winds is too strong. So we need to always consider the wind speed and also wind direction. And this is the illustration of why the image overlap is necessary. For example, here we set the flight altitude to 300 feet or around 100 meters. Here it will provide us like 60% from overlap, and with 60% of overlap we will have good states that we have. For example, there is one object here. We will have one object that captured from 4 different angles, so we can reconstruct the whole image or the whole area that wait, let me just this one. So we can get the image in this area. You can reconstruct it's perfectly because it's covered from 4 different angles. But we need to consider when we are how to say, when our mission is covering a broad area, that the topographic is something like this, for example, mountainous, because whenever we set 100 meter from here, from the lowest level, the altitude will be diminished here because it will reach to the area that is higher. Therefore, the side overlap and also the front lap will be diminished or it will be minimized. So you can only have, like, for example, here only one image that can be reconstructed only from one angle. So it's quite difficult to reconstruct. That's why we need to consider the highest altitude, or the highest ground, the highest ground altitude when we are setting the flight altitude. This is really necessary. Otherwise, you will have like the image that will not have front lap and also side lap like this, and we cannot reconstruct the orthomosaic image, something like this. This is the formula when we need to have a specific ground spatial distance. Ground spatial distance is the lowest pixel size. For example, when we flew our aircraft lower, it will provide us a higher image quality, higher spatial resolution. But when we flew our drone higher, it will provide less spatial resolution. Therefore, we need to set our flight altitude into like which accuracy that we need, or which ground spatial distance, something like this. This is the illustration how the UAV capture the risk area. For example, suppose that this is the risk area and this is the fixed wing. It will fly following the flight route that we already set, and it will provide some picture like this, aerial image like this. As you can see here, the aerial image is overlapping each other. You can see similar image from different angles, something like this. And the second one, we need the ground control point that we measure using markers. We install markers like scattered in the whole area. We can use it should be clear, that really visible from the aircraft or from the air. As you can see here, the shape of the marker is like this, the cross with light colors, with orange, for example, so you can differentiate the color with the land use, with the surrounding land use. But in some cases, we also can use a pattern like this, because whenever you put this color, for example, on the ground with gray with a brownish or reddish color like this is not really visible, so we need to have a different pattern or different color like this, so we can easily recognize it in the aerial image, something like this. And when the markers are not possible, for example, when you are flying too high, that the markers is not visible, we can also use a post marker. So we measure like some how to say, for example, buildings or roads, or the edge of the road that easily recognizable from the image, so we can use the coordinates for georeferencing purpose. This is the georeference, something like this. We can use this pattern, and it should be installed like how to say, evenly distributed. It should be evenly distributed in the whole area, because we need to use the coordinates from each point, and we use the coordinate for georeferencing the image. So we will have only small errors from the image generation, because here in this case we need to provide high accuracy geospatial data. For example, here in our project, we have 10 ground control point here that evenly distributed in this area. This is Baron Beach, one of the most popular beaches in this area. For example, here in the in different case, for example, we are uh, capturing the riverscape like this, because in this research we are modeling the flood in this water site, in this water set. So the configuration of KCP is a bit different when in this first in this first area is evenly distributed, like in the corner and in the middle, and with different elevation. But here it's like following the shape of the river, because we need to provide more accuracy alongside the river, something like this. So it's always depends on the area that we want to map. This is the example of the data input. So whenever we measure the coordinates in the marker, we take a picture in 4 different directions, something like this. Like we have the indication of direction. U is utara in Indonesian language, or north direction, and this is south. For example, selatan is south. And when we input the coordinate into the software programming, it will looks like this. For example, here you can see this marker, and it's located near this tree. As you can see here, you can just verify the figure on the picture from this picture. So the people that are in charge in inputting the coordinate will be highly helped with this checklist, something like this. For example, this one in the southern direction of this marker, you can see this hill. So this is here, and here behind this girl is this coconut tree. Here it's located in the north, something like this. So you can easily input the coordinate, even though the people that in charge is in inputting in inputting the coordinate is not joining the field work, for example. So this is the result in some of the beaches. This is Baron Beach. This is Sepanjang. This is some popular tourism beaches in the area. We provide high resolution spatial data. This is the example of the data processing. So from the overlapping image, we create a point cloud. So the software will detect the picture with similar pattern, similar color tone, similar altitude, and it will construct this point cloud, something like this. And then furthermore it will something like this here, here. And this is the main products of the UFV photogrammetry. First one is automosaic image, something like this. And we can also generate digital surface model, something like this. And we can also create a contour map. And furthermore, actually, we can also provide something like this. For example, this is the digital surface model from the UAV photogrammetry. And we can also filter the land use here. So we can remove all the land use here, like buildings and also trees and so on. So we can have a digital terrain model, something like this, and also contour map as well. This is the difference between a digital surface model and also digital terrain model. This is sometimes this is necessary for modeling, because the modeling results will be also affected by the existence of the land cover, especially in hydrological modeling, for example. This is not only for tsunami, but we can also use it for coastal flood, or even for river flood. We can also use it. This is the difference between digital surface model and terrain model. For example, like this, this is the illustration. The digital surface model, it covers all the land use, like what is visible from the camera. We can generate digital surface model here, and with some specific software, we can remove the land use, so we can create a digital terrain model. For example, this is the difference of uh, the appearance of DSM and also DTM. This is the cross section. For example, if we make a cross section here, it will show us like this. The blue one indicates the digital surface model, and the red line indicates the digital terrain model. So it removes the land cover, something like this. This is also same illustration, something like this. And using that digital surface model and digital terrain model, we can create a hazard map, tsunami hazard map with different scenario, something like this, based on the previous or the recent studies from the Department of Geophysics and how to translate in English? Department of Geophysics and Meteorological of Indonesia. The southern coast of Java is how to say it's like we are it's a prone area that a huge earthquake might be occurs from the megathrust, and this earthquake will trigger like 12 meters run up from the coastline. So here we try to model that run up with a different run up scenario from 4 meter to 12 meter. Like this is 4 meter, for example. This is 6 meters, 8 meters, 10 meters, and 12 meters. This is in Trini coastal area. This is in different, and its location will have different impacts. For example, this area is like this, but this is the area that located in like very flat bay. Here it's actually this area is located in the karst area, where there are so many hills here, like conical hills here that can be natural barriers for the tsunami. But in this beach, for example, it's located like in the flat area. So even with only 4 meters run up, it will highly affected by the inundation, something like this. So that's why this is necessary. This is necessary to provide high resolution spatial data, because this model will not be covered by the model that provided by the government, since they are only providing low resolution data. For example, this is 4 meters and this is 6 meters, and this is 8, this is 10. The conclusion is this area needs to be, we really need to pay attention in this area, because the area is considered really prone to the tsunami hazard based on this model, for example. And we also propose the evacuation point, since the evacuation point that provided by the government are ineffective. We use the inundation model, the run-up model, and we also provide buffer, something like this. And we propose a tsunami vertical evacuation, because the most important thing in tsunami evacuation management is we need to find safe place in order to save lives. So after maybe the tsunami occurrence is how to say takes time, you will have more time to relocate to safer place. But the first thing that is really important is to find safe place. And the important thing in near field tsunami is tsunami vertical evacuation. So you are not aiming to the area that located far from where you're located, but you are going to the place as high as possible where tsunami cannot reach you. So we propose the area that could be used for temporary tsunami vertical evacuation, like this. So based on the this run-up model, we propose some area that can be used for tsunami shelter, something like this. So actually we calculate the travel time to tsunami vertical evacuation using the digital elevation model that provided from the UAV photogrammetry. We use ArcGIS, so we can calculate the travel time. And here, for example, we have the beach location here, and we have proposed tsunami evacuation point. We provide evacuation routes based on the area that can be accessed the fastest with the lowest time travel, something like this. So actually, this is another illustration for the whole area, something like this. This is the illustration. This is the tsunami run up or invasion zone, and this is the free port or buffer, like 30% from the run up, and the area that are not covered by the inundation model, and also the buffer is considered as safe place. So we can propose evacuation point in that in those areas. For example, here in the whole area, we propose 14 tsunami vertical evacuation point. Sorry, yeah, 14 to 15, if I'm not mistaken. Here, and this model we use wait like this from here, and the travel time is calculated from the Doppler hiking speed, or the speed of people walking on foot. So we calculate the average walking speeds of an adult, and also we also consider the land use and the land cover with the, how to say, like coefficient, money coefficient. So when the land use is covered by, for example, like this, when it's covered or the land use is road or pavement, it will be, how to say, it will provide faster time travel. But when the area is covered by marshes, for example, or high density trees, it will provide less travel time. So the model will give us the shortest time travel to the location, like this. And this is the white line indicates the most effective evacuation planning that provided by the software. But later on, of course, we need to also validate the model, because sometimes it won't work when we try to, how to say, to validate the model with real tsunami evacuation uh, planning, or uh, something like this. And beside, because here we are also talking not about the hazard, but the disaster risk reduction in the whole context. So we are also considering the environmental vulnerability, and we are also calculating the loss estimation as well. So for example, based on the different run-up scenario, so we will determine like the area that are affected by the tsunami. For example, here, the area that affected by 4-meter tsunami scenario will cover like 4.28 hectares of agriculture area, and 0.21 of fish ponds, and with different scenarios, it will cover a broader area of course, like this. For example, here in 12-meter scenarios, it will covers 23.51 hectares of agriculture area. Which this is really necessary, because we can determine the areas that are vulnerable from the tsunami inundation model, so we can also determine the risk, and we can also census the people that live in that area as well, based on the number of houses. We can ask the, how to say, the government in the lowest level, like how many people are living there, the data, how many people are exposed, and their age, their gender. So we can also create a social vulnerability. But this is still ongoing, so we are still working for that, because sometimes it's quite difficult to access the how to say, the data from the local government. And based on the size of the area that are covered or affected by the tsunami inundation model, we can also calculate the potential damage, and we can like evaluate it, or how to, what is the right term, we can calculate like how much is the damage. We can convert it to euro, for example, or to rupiah, to our currency, something like this. For example, if the agricultural area covered by 4 point for example, 4.2 areas of agriculture covered by or affected by the tsunami, it will give us like 342, this is in million if I'm not mistaken, million euro of damage, something like this. So this calculation was done using like land valuation. So we go to the field and we ask the price of the land and the price of the buildings, like how much they spend to build, like for example, temporary buildings. So we value it that, and we convert it to money value, so we can determine of the effect or the damage if just in case the tsunami occurs. And this is really important. This is necessary because we can determine the risk, and we can also propose to the government for the for the for the disaster risk reduction planning, because with this model we can understand which area should be prioritized for disaster risk reduction planning, something like this. This is the example of the land use delineation from the aerial photograph. And the other thing that is also necessary is we can provide really accurate time series analysis using high resolution spatial data. For example, here, this is the aerial photograph of the last beach that I show you, the Krakal beach in 2015. And because UAVs provide, how to say, we can conduct our project like how to say, with 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 short interval. We can take the aerial photograph like each year, or even every month. For example, here this is the aerial photograph that taken in 2015, something like this. And then this is 2017. So you can see there are a lot of difference in this area. This one 2015, this area is mostly agricultural area. You can see corn pattern here, and some are paddies here. But in 2015, the whole area is changed. There are new cottage here as well. Like this is tracks for, I don't know, it's like for racing, something like that. For, and in 2018 it changed again, something like this. And 2019, and at the moment this area is a bus terminal, very large, very huge area of bus terminal. And here as well, the settlements are expanded. The new hotels built like this. This is 2015. This is 2017. You can see some development here as well. For example, here, this one, it wasn't there, but right now I don't know what building is that. But here on the corner, you can also see new fish ponds, only in matter of a short time. So you can also analyze the rapid land use change in this area, and this is also necessary for planning, because when the settlements are expanded, tourism facilities are increased, therefore the vulnerability is also increased because there are more people at risk, and also more buildings, more infrastructures are also in a vulnerable state. And at the moment, we are also working to provide multi-hazard assessment. So beside, we are working on the tsunami hazard mapping and also risk reduction regarding to tsunami hazard. We are also concerning on the other hazard, which is rip current. Rip current is actually, even though tsunami is like one of the biggest threat in the coastal area of Java, but in the real situation, the disaster, or how to say, uh, rip current is the most how to say dangerous, because there are hundreds of people drowned annually, and tens of them were dead. For example, just like a few weeks ago, three, or no, sorry, two students were drowned, and both of them died, and the other one just they can found the body after 10 days. So rip current is a really serious matter in the coastal area, especially in the area of Gunungkidul, where tourism is really popular, because so many tourists that how to say spending their time in the beach area like this, they are not really aware with the rip current. First, because they are not really familiar with the area, because most of them, they are coming from outside of the region, so they don't have any knowledge if the area is dangerous or not. Even though there are SAR or rescue team there, but sometimes the tourist is just how to say, it's quite difficult to organize that many people that located in the same area at the same time. Uh, and second, it could be occurred really fast, the rip current. Before you realize it, you already drown. So here we try to map, or to determine in which area the rip current is located, because in this area, the coastal area of Gunung Kidul, which the area is mostly formed in the karstland from, so you can see that most of the coastal area is how to say, this is the coral, or the reef is there, and most of the reef currents is persistent, or not moving. In some beaches that mostly form in the sands, they are moving, depends on the bathymetric condition, and also depends on the wave height. But here in Gunung Kidul area, the rip current is mostly persistent, or located at the same area, because of the existence of these coral reefs. So normally they are occurs in the area that are not covered by reefs, where the sand is how to say, when the sand is available, enough sand is available, and the depth is also sufficient to generate rip current, something like this. So we inject fluorescent dye. This is uranin. Uh, this is made from sodium, or from salt, basically, and it normally used for water tracing in a cave. For example, if you want to determine the cave network, you inject this fluorescent dye in some specific place that located in the sinkholes, or in the upper part of the catchment area, and it will flows following the underground river, and you can detect in some where you can easily recognize from the color. So you can conclude that, for example, the springs or the caves are connected to each other. And we use that kind of chemical compounds to map, or to determine the flow of the rip current, something like this. So we pour fluorescent dye here, and it will be follow the rip current, something like this. So we also capture it using drone and something like this, something like this. So actually rip current is like a really narrow current that the speed is really fast, even though people with uh, different, how to say, like, even though you are a professional swimmer, for example, you will be still sucked by this current, because this is really fast. And we try to propose the hazard map, or the area that considered dangerous for rip current. Uh, for example, like this, because rip current is generally only narrow, something like this. When we measure the width of this rip current is only less than 2 meters. So actually, we also disseminate to the people, to the tourists. We make a campaign that they should be aware with the coastal hazard, like tsunamis and also rip currents. So we ask them whether they know or not how to escape from rip current, for example, and we show them this picture. Actually, rip current is really narrow, so